Welcome, everyone who is joining. We'll give it a couple of seconds while I'm beginning. Um, this is our session on space agency analogs and simulations. It hosted by myself, Terry Trevino. I'm a adjunct professor here at the American Public University. And we're also here with Dr. Arnold Nikogassian. And then we're also here with Dr. Kristen Miller. And we are currently spread out across the United States, but here we are today and happy to see everyone. What we're going to do is we're going to start with an introduction on the two other attendees, and I'll do a quick intro on myself. I'm really here to moderate, answer any questions on the chat. So if you have anything you want to ask, I'll keep an eye on that. And yeah, here we go. We will start now. With us today, Dr. Kristen Miller. Dr. Miller is one of our premier professors at the university. She gives us quite a bit of direction as it relates to the several different functions, and in the meantime, she also helped us with our analog research group. We founded here in 2021. I was one of the co-founders with Dr. Miller and another gentleman by the name of Scott Van Ooy. There was other participants, but they've moved on, and here we are today as kind of the remnants. But we are finding quite a bit of success in the analog world, and as our friend Diallo Wallace, also a professor, has always said, you need to test before you invest. And here we are. We feel like analogs are the best test environment for understanding how we might work and off-world. Frankly, if you think through it, what are the methods? What are we going to look for? What are some of the safety protocols that we'll have to have in place when we step out of our habitat? And we practice all of those with our simulations. And Dr. Miller has been wonderful in leading us in that endeavor for the past several years. She's also a teacher at the university, and as a professor, really kind of runs the entire program for us. And then we have Dr. Arnold Nikogassian. And Arnold, I'm just going to say Arnold because I love your name. And as it goes, he's been with us for years as a professor, but he also had a previous career at a little known space agency. I believe it was called NASA, and they were instrumental, obviously, in getting us to the lunar surface. And Dr. Nikogassian was a part of that endeavor, and has been on the medical side of that, and was I believe the chief medical officer for NASA for many years. And now we're lucky enough to have him at American Public University as a professor. And whoever has the opportunity to have him teach you, just remember how amazing he is. And then myself, I'm a graduate of American Public University, American Military University, and I'm a master's in aerospace science. I'm at the University of North Dakota in a PhD program, but I'm still an active member of the analog community at APUS. And we have an ongoing mission right now, which is why I was here at the University of North Dakota. And we're going to continue on that. And we've got plenty to talk about now. But I'm going to start with you, Dr. Nikogassian. If you want to start your soliloquy on the slides, I'd like to let you just run it. It's all yours.
Thank you, Dr. Trevino. Appreciate your
Not a
introduction.
doctor yet. Thank you.
Whatever.
Yeah, thank
future
you.
doctor. You deserve to be a doctor by now. All right. Just want to let you know that I joined. I was always fascinated with space. And the reason I was fascinated is because the late Chuck Berry, well, it was before Chuck Berry. I was fascinated because I loved astronomy and antiquity, and the origins of life were always of interest to me. The other thing which was really fascinating is that as a kid, I was reading all those astronomy manuals, and I hope you will not laugh and think that I'm very ancient, which I am. I really believe there were canals on Mars. That goes back to Schiaparelli, and I know Kristen as Professor Miller is already laughing, but that's okay. I will forgive. But anyhow, you know, I was given by the French government the opportunity to go into aerospace engineering or astronomy. And the fate was that my mother decided she will send me to the medical school. So I went to the medical school and became a physician. And after I came to the United States, I decided, hey, you know, learning about the effect of the environment on the lungs and things like that, and loving to fly, I decided I'm going to apply for aerospace medicine training at Ohio State University, which is now closed. And then NASA picked me up and invited me to Johnson Space Center to be working there as a cardiovascular researcher. And my first mission was Apollo 17. It was very exciting because I was never a seafaring person, and I found myself on Navy aircraft carriers fishing the astronaut in the South Pacific. If you have not been in the South Pacific, I recommend you do it. And it's nice, but not on a Navy aircraft carrier or marine carriers with helicopter land platforms, because there is no porthole that you can look through. And during the drill, the Z doors get closed and you feel very isolated and stressed out. But anyhow, besides that, so it dawned on me from my medical practice treating patients that we have patients who are sick in a normal environment. I want you to remember that we take healthy people and send them to space and make them sick. So in an abnormal environment. And finally, when I started to grasp that, I understood that from my training as a physician, that too much of anything make you sick, too little of anything make you sick too. And just the right amount of your environment make you happy and healthy. Just think about oxygen. Oxygen is a drug, but oxygen is needed for life. Okay, too little oxygen, you get anoxic. Too much oxygen, your lungs burn out, if I want to tell. And, we can go on and on. Also, you need to remember, when I walked into Johnson Space Center and started working them, there were too many, I met too many analog and habitats and simulators and things like that, which was awesome at that time. And they expanded since then. So with that introduction, I would like to start the presentation. The reason I said it is because I'll be talking what analogs are good for. And they might be good for many things, and not so good for other things. And please remember, when the program started, it was before me. People were worried about things. Can you urinate in space? Can you eat, swallow in space? Can you maybe scratch in space? And the first thing that people did is to simulate space environment that there were parabolic flights. We still use them, and it's commercial now. We still use those, the parabolic flight where you have so many parabolas. At some point of time, you get motion sick. And there are all kinds of stories I can tell you, but not now because we are limited in time. So keep that in mind. Okay, Some of the material is copyrighted. That's a view of Earth as seen by our keynote speaker. And some of the material, a lot of the visuals are from NASA. Some of the material are copyrighted to our textbook. Dr. Miller is working with me on that textbook. But there's no conflict of interest to receive. APUS did not pay me for this discussion, neither did NASA. Okay. So what's the objective? I would like to discuss simulation and training facility used by NASA and international space agencies. All right. Here's some definitions. Space analogs are ground or space-based facility offering some or all of the extreme conditions of space. So we want to see if we are going to make people sick, really. Space simulation is a replication of one or more parameters of the space environment applied in testing of the space systems or component or humans, which are part of the components. Often a closed chamber is used capable of approximating the vacuum and normal environment of space. Let me tell you, when I first saw the NASA high bay hyperbaric chamber, it was awesome. You can put the whole Apollo spacecraft. You can really pump it down to almost zero vacuum, to total vacuum. And it has a lot of headlights to simulate the solar warmth or turn off one side or the other side or the darkness of space. And people were doing EVAs there, simulating moon and things like that. And I still use now that the moon is coming. Astronaut training facilities are generic or specialized high-fidelity mock-ups used to teach skills necessary to operate spaceborne systems. Okay, so let's go further and see what we see. You've seen that slide. I always love to use it. It's in my textbook. I'm very proud of it. The first time I had the ability to express my opinions about, thanks to Dr. Miller inviting me to those sessions, to express my opinions about different analogs and simulators. Remember, in space, we are not inactive, we are active. Nobody lays there in a corner, unless they're very depressed, that's when we know. Lay in the corner, right, okay. They either exercise, they move around, they eat, they do. They are not inactive. So when you talk about space inactivity and simulation, that might be a misnomer. Be careful to clarify what you mean by space inactivity. So in red here, this basically says that that isolation, remoteness, hazardous, and extreme conditions are common throughout all the analogs on Earth, including the AARG program. What do they measure? They measure psychological interaction, multicultural compatibility training, and studies of experiment and testing of equipment and failures. That's important. Then you go to microgravity. Analog is high fidelity. I'm just highlighting in red the high fidelity. International Space Station is a high fidelity, but it doesn't replicate the interplanetary space radiation. Okay. Day-night cycle is high fidelity, and light-day cycle has been used to adapt the astronauts. And we have a chamber, a special actilums system worn by the astronauts, and different light-dark cycles that we adapt the astronauts, because we launch them in midday, we launch them at night, and the time when they reach the space station or they reach going to orbit might be entirely different from the time that is on Earth. Okay, So here that is, you can go to the book, APUS has the book, your library probably has that book, Space Physiology and Medicine, and learn from it. So since I was at NASA, and I will show you if time permit, how I'm doing. Hello, I am doing on time.
Plenty of time, no problem.
Okay. So NASA contracted a place next to between Houston Residence and Austin, Texas. And those guys are specializing in 3D printing. And that's the beginning of the CHAPIA, which is a Mars analog 3D printer. If you wonder, where did they do it? You know, that CHAPIA, we just finished over 328 days or whatever. It's located in a hangar. But the simulation is so good that you think you're on Mars, except there is no microgravity. I'm not sure if they had radiation sources, but the experiments had not been published, and I'm not checked with NASA, but I think there was a radiation source to check some special materials as protection materials. So it's the name CHAPIA is Crew Health and Performance Exploration Log. These are the people who went in, and they entered June 6, 2023, July 6, 2024. They simulated everything. The communications were difficult for them. They were growing their own plant. I'm not sure they grown spirulina or not. Kristen, probably they didn't talk to you all, but I'm sure they will start growing it as soon as they find it. And here's the living quarters or work quarters. And it's an interesting place, okay? So it evolved, the whole thing evolved. What are the other facilities which are there? Well, you know, some of the facilities is simulating microgravity in different directions, acceleration. These are the mock-ups for everything. You train these mock-ups, you get the skills, you use the manipulator, everything is simulated except gravity, microgravity. This is the parabolic flights. This is the water immersion facility that it's one of the biggest water tank when you have the whole space station mock-up in there. And that's the extravehicular activity planning. It's called after one of the physicians, astronaut who died in the airplane crash, Sonny Carter, great guy. And people are wait here, so they will be buoyant. And there is also those divers who kind direct them on the practice, getting in and building, putting solar panels, etc. One of the things which was all of, if you ask what the flight surgeons do, they don't sit only on the console and worry about what's happening in space. They also follow the astronauts and when they train. And, the astronaut trained for about a year or so, and then the practice before the mission for several months. This is the water irrigation facility, and there were all kinds of problems originally, which we'll talk later on. Okay. International Select, Russian Federation IBMP has isolation and human factors. That's underground. That's on the premises. It's a kind of combination. It's a biomedical facility, basically. A human space, human factors. They did a 520-day simulation. One of the simulations which involved international crew, which had a woman, they had to break it because during a party celebration during New Year, some of the crews get drunk and kind of harass the woman, astronaut or the woman participant, and they had to open the door. And some of the luminaries made the conclusion, not ours, that we should not send women in space, but that's because that creates discord. Good for them. So it's culturally diverse crews, Russia, ESA, and China, did either hire them or participate in them or invited. Amadia is a Mars simulation. It's run by the Austrian Space Forum, hosted in a 4-week Mars analog mission in Armenia. Please learn how to pronounce my last name. Okay. So I'm just kidding. And PRC, China, has a Mars simulation that they built since we visited them, because the space program basically not only is military, but is also located in China within the Chinese Academy of Sciences. And we were probably the first foreigners to visit them. In late 1990s, we tried to open collaboration with them. And obviously, when there was a collaboration, they wanted to show benefits to the public. So they used to send as a forward boarding party physicians and biologists. They still do that. They still do that for Artemis. And we went there, and it was a lot of borrowed from the Soviet era program. And what was good, I don't know Chinese, but I was so happy to be able to communicate with those people. And you know why? I spoke Russian, they spoke Russian. So we could talk without interpreter. It was good. Made everybody else annoyed, but and I couldn't do it today because everybody at Johnson Space Center, Kennedy Space Center. So they do have also facilities for simulation. I will know more about those facilities because Chinese one in the mainstream now of space exploration and competition, and they invited many nations to participate in their Tiangong mission 2, Tiangong 2. Okay. So what those things did for us? Apollo 1 fire, which was a result of the bolting and latching the exit hatch that you couldn't open very well from inside, and you had to open it from a special tool, was adopted after the incident in the Mercury, when the explosive bolts blew up one of the Mercury capsule hatches, and that thing sank. Okay, they just recovered. Skylab was an altitude chamber test. What was tested? Primarily orbital replacement unit exercise. And the guy who was there, Bill Thornton, a physician, he worked with that equipment, and finally he broke the bicycle ergometer, and we had to send. We learned about that, so we sent spare parts, and the things worked in space. Space Lab. It was a 7 to 21 day simulations at Johnson Space Center again, and in that simulation, we tested the use of biological specimens, animals, and the design of the animal holding facility. And those were designed, and some of the animals. NBL, I talked to you about neutral buoyancy tank. Not only you learn something, but we went and fixed the problems with the current EVA suit joint and glove. They were redesigned because they were injuring the fingernails, the tip of the finger, and they were injuring wrist and shoulder joints. So the current suits which is being used is a much more safer as a result of that. Just a few examples for you to look at and to remember that simulation is on human factors is very important because you can test equipment all over the place. Okay, and that's all I had to say, and thank you for listening. If you have any questions, I will be more than glad to answer those when Dr. Trevino or future Dr. Trevino will allow us to do so.
Thank you, Arnold. That was amazing. Great detail too. Thank you very much.
I could
Dr.
say,
Miller?
I could tell more, but we don't have time.
No, you're right. Time is always a very expensive commodity, as they say. Dr. Miller, do you want to go ahead and rock and roll?
Sure, I'm happy to do that. Should we save all the questions for the end? Is that what you're
Yeah,
thinking?
that's all right.
Perfect.
Yeah.
Yeah, we can do that. Yeah, let me share my
I think
screen
if you just
here.
hit share, it might take over. Let's see.
I think it does. Yeah.
Yep, there you go.
Perfect. All right, let me get the right mode here. All right. Well, I'm happy to be able to talk with everyone today, and thank you, Arnold, for a really amazing and so interesting overview of the way that analog research is used by NASA and other international agencies. I think it's really exciting that we have these analog habitats and environments and training facilities that allow us to do research that translates into the space environment and helps us to prepare for space exploration. So my part in this panel is to talk to you about the kind of the flip side of that. We've heard about the NASA and official use of analog habitats, and I'm going to talk to you about the way that commercial and slash private companies slash academic institutions use analog facilities for research. So like Arnold said, an analog is a structure or an environment that can mimic some aspects of the space environment. Of course, it doesn't mimic all aspects of the space environment. If it did, it would be the space environment, but we can mimic at least some of them. And in general, there are 5 challenges of the space environment that we try to study with analog habitats and things that we have to consider when we think about living off-world. And the first is radiation, because in a space environment, a true space environment, we're living beyond the protection of our magnetosphere and atmosphere. So we're fully exposed to the radiation of space. Isolation and confinement. This is intrinsic to any space habitat, something they all have in common. Distance from Earth is a factor that many astronauts have noted and that can cause some psychological effects. Gravitational fields. As soon as you leave Earth, then you're exposed to, and during space travel, you're exposed to many different gravitational profiles, all the way from microgravity when you're in transit or perhaps in orbit around a planet or a moon, to the non-terrestrial degrees of gravity that exist on other worlds, such as, for example, 1/6 Earth gravity on the moon, 1/3 on Mars. Every planet will have its own unique value of gravity, how the human body reacts to that. And then the final challenge is that the hostile enclosed environment of space. This is the idea that if you were to step outside the habitat without protection, basically you wouldn't survive, right? The high risk that is inherent in the space environment due to its lack of life-supporting characteristics, it's real. And living with that risk poses psychological challenges for the crew. So when I think about habitats and analog habitats, what I'm going to do is talk about some analog habitats that are available for commercial use for private individuals and for academic institutions. And in my head, I kind of divide them into 5 different groups. The first is space-like structures. These are kind of the traditional habitats that we think of when we say analog habitats. And I've just got some images of some really interesting ones here, some that are pretty cool. The top left is the MDRS, the Mars Desert Research Station in Utah. We've got Flashline Mars, which is up in the Arctic. Lunares is an analog habitat in Poland. The one on the top right, that glowing dome, is high seas located in Hawaii. And of course, the bottom left here is ILMA, the ILMA habitat in North Dakota, where the APUS Analog Research Group is currently undergoing an analog mission. So that's one of our favorite. Each of these habitats, they're designed to be space-like. Each is enclosed. It has, when you're living in the habitat, you have very little view of the surrounding terrain. And these mimic the isolation and confinement of space. You're living in very close quarters with your crewmates. These structures and habitats are located around the world and throughout the United States. The second group is underwater facilities. These are unique and high fidelity, high risk facilities where very interesting research can be performed. Again, you live in these structures, so they are habitats in that sense. The premier is, of course, the one pictured in the bottom left here, the Aquarius Reef Base located off the coast of Florida. Some really amazing analog research has come out of this facility. Unfortunately, it is not currently in operation, but we hope that it will one day soon return to its operational status. It's a truly unique and amazing research facility. On the right is a picture of the dock at the Jules Verne Undersea Laboratory, where this is where the crew will don scuba gear. In each of these underwater facilities, you access the habitat by diving underwater in scuba gear. You access it. The access point is actually underwater, and the crew lives underwater for the duration of the mission. And this image is actually a couple of members of the APUS Analog Research Group donning scuba gear and getting ready to begin their 2-day mission that they completed last January at Jules Verne. And the top left here is an image of what the Proteus underwater laboratory could be like. This is a conceptual design. It's in the development stage. It's spearheaded by Fabien Cousteau, who is the grandson of Jacques Cousteau. But the thing that's really unique about these underwater facilities is the fact that not only do they replicate the isolated and confined environment of space, but they also are higher fidelity in that they are able to give you a feel for the hostile environment. There's real risk, no easy exit to these facilities, and real risk when you come outside of them. Due to decompression sickness, especially for those that are located fairly deep in the water, like Aquarius and Proteus could be. They also you can simulate some gravitational effects, not inside the habitat, but during EVAs due to the buoyancy force and using systems of weight. So interesting facilities. Then we have research facilities, and Arnold alluded to some of these. There are also, in addition to our favorite, which is of course the ISS here in the top left, there's also McMurdo Station in the Antarctica. This is a picture on the right of the Neutral Buoyancy Laboratory that NASA maintains, but there are also similar buoyancy pools that are used for research at academic institutions across the country, and even some that are commercially owned and accessible by commercial entities. These research facilities, they're designed with the specific purpose in mind. They are typically very high fidelity, and they're able to mimic the targeted aspects of the space environment very accurately. They are frequently high risk as well. So all of these can, especially McMurdo Station and the ISS, they can mimic the isolated and confined aspect of space as well as the hostile environment. The ISS, of course, is our laboratory where we are living in microgravity. So we're mimicking the gravitational fields of space, and to a partial degree, as Arnold noted, to a partial degree, some of the radiation atmosphere, although it is still within the magnetosphere of the Earth. It is pretty high up and above most of the atmosphere. So there is some radiation exposure there that you don't have under the protection of the Earth's surface. The next group is submarines. These are really interesting because so many people live on them, hundreds of people at a time. So there's the possibility of doing what we like to call high-end studies, which just means a study with a large number of participants, which gives you really good statistical data. They are definitely isolated and confined environments. They are hostile and closed environments, and that there's real risk and no easy exit. They're also typically long duration studies, very high fidelity, but typically very little opportunity or freedom to propose and conduct research studies. However, there is lots of good data that has been taken on people who live in submarines and their mental state and how they operate. And a good share of it is in the public domain and can be used to support research, especially human factors studies. So I include it because it can be used in commercial research. And finally, analog environments. So these are the least like the traditional analog habitats that we usually picture. These are they can be expeditions. The top left, this is an Arctic expedition, or the top right, this is Everest Base Camp. Mountaineering, hiking expeditions can be thought of as environments, sorry, as analogs, because they do occur in hostile environments and they have exposure to those environments. Here in the center, I picture a ship because long duration sea voyages where you are isolated and confined. And again, it can be in a hostile environment. The bottom right, military deployments. These have a large number of people in what is frequently a hostile or high stress environment, often with very little contact or communication with the outside world, and where danger is real. So these, deployments certainly qualify as an analog environment for the hostile environments of space. And then finally, the parabolic flights, which, not only does NASA use them, but they're available for commercial use as well, where microgravity is simulated. So there are a lot of different analog habitats, analog environments, analog testing facilities. They're cool, they're interesting, they're unique. Why are they important, right? Well, they're important because they can support research that is relevant to space exploration. So there are many types of analog research that can be performed in these habitats. The thing that's really great about them is that analogs are typically low cost, they're flexible, they offer highly efficient operations that can simulate actual space missions, because many systems and subsystems at various stages of development can be validated at the same time. So they can give you some really interesting data and some really important testing opportunities. When you test in an analog environment, you can account for the effects of stress and isolation on crew performance, right? Some people say, well, we can test technology anywhere. Why do we need to test it in an analog? But when you're testing it in an analog, you're testing it while the people doing these, using the technology and doing the operations are under the effects of stress and isolation. And that does affect crew performance, and it does affect mental capabilities and decision-making and teamwork and just many aspects that are so important to the success of a mission and to the use of these technologies in a real space-like environment. So there's a lot of important information to be gained by testing them, not just in a pristine laboratory setting, but in a realistic analog environment. And I just listed, just off the top of my head, this is by no means a comprehensive list, but just some of the different types of research that can be done in an analog environment. And you can see that it is diverse, it's far-reaching, everything from human systems interactions and protocol development, all the way to human factors studies on the individual participants in the analog, their diet, team dynamics, physiological studies, how does the body react in these high stress and isolated environments, as well as habitat studies, studies of the logistics and flow. How can we optimize habitats in order to best accommodate human habitation and human research and workload, communication studies, astrobiology and plant studies, geology and field studies, and of course, medical studies that are so important for success in the space environment. So just a quick list of some of the wide array, just give you a taste of how far-reaching and how diverse analog research can be, and the many different things that can be done in an analog habitat. So what are the advantages of analog research? Well, the first one is that you can get a larger participation for the studies. We have many more people can participate in analogs or in analog testing than will, fly on the ISS in a given amount of time. And you can also run tests repeatedly, and you can run a wider array of variables. We have lower cost for the testing. The analogs, it's greater availability. You can plan a research project and develop it and actually run it and start getting data in maybe 3 to 6 months, as opposed to a much longer time frame to do it in an actual space environment. Greater flexibility with less red tape. That's always a good thing. You can also, test sustainability practices and space technology utilization. There's, lots of practices that can be tested that are essential to efficient and safe mission planning, which can be tested on the ground before you're in an environment where a single mistake can cost human lives. You can test it in an analog setting so that we are not, where you're in a safer environment, safer but still realistic. It can also provide important data to guide policymakers and mission planners who would otherwise be making decisions with very little data. So lots of important reasons to do analog research. What is the impact of analog research? Oh, I'm sorry, whoops. So in my head, the three important impacts, the three most important impacts of analog research are that it inspires interest. I think there's a lot of interest in space exploration right now, a lot of people who want to be a part of it and who want to get involved. And analog research is a way that people can get involved in analog research. Not everyone who is able to, who is interested in making an impact in the space community will become an astronaut, but everyone who is interested in making an impact can do research here on Earth that will make space travel possible and that will develop the systems that will lead to humanity becoming establishing an off-world presence. I think the analog astronaut community, which holds their conference every year, really shows the amount of interest that there is and the diversity of people who are interested and want to be part of the space community. Analogs give you a chance to do that. And they give you an opportunity for people who might not otherwise have that opportunity. And it's important to inspire that interest. It provides support for all kinds of space exploration and unites us as a space community. Analog research is really valuable from the academic side. Analog research can provide data and opportunities to perform research that can lead to thesis projects, both at the master's and doctoral level. As well as providing research experiences to enrich, curriculum and classroom learning. It's also an opportunity to perform hands-on research and to perform team-based hands-on research. And team-based it's a big thing in scientific research today. And an analog is a really natural way to be part of a research team and to be part of a crew that's performing the research and that is relying on each other. It teaches a lot of skills in terms of working together for a common goal and how do you, accomplish the research goals and achieve success in this non-ideal environment. So a lot of real benefits in an academic setting. Commercially, there's also opportunities for name recognition and to gain a competitive edge to start collaborations with NASA. One example, the APUS Analog Research Group this past year collaborated with a commercial entity to test some of their technology during an analog mission. It was really great for us to have the chance to have this really high quality equipment that we could test in an analog setting. And it was really great for the company to be able to see how their technology worked in the analog setting and with, realistic spacesuits and how it integrated into that, and as well as getting some really great PR pictures out of it. So, both important data as well as a really good name recognition for them. So there are many advantages. NASA not only does their own research, as Arnold has talked about so well, but they're aware of private analog research and they're interested in it and they support it. They provide funding through the Planetary Science and Technology from Analog Research Program, which has funding opportunities for research that is basically focused on technologies that will help us to that can be developed on Earth and that can be applied in an off-world settlement and in terms of planetary exploration. There are also space grant consortiums which exist all over the US and cover pretty much every state in the US. These are partnerships between academic communities and NASA, which provide funding for research, much of which is conducted in analogs, or at least can be conducted in analogs, and that answers NASA's questions, the big questions they're trying to answer to get us to the point that we're ready to go back to space and to stay there. NASA also supports collaborations. They collaborate with many universities and collaborate with university research in order to accomplish these goals. And they provide support for private sector partners as well, not just academic. In fact, 85% of NASA's budget goes to private contractors who are doing research for NASA. They also provide opportunities to perform research on the ISS. Those are available to commercial entities as well as academic and even private sector partners who develop research projects and want to try them out actually in our most high fidelity analog, the ISS. NASA also supports commercial astronaut activities. So they have a lot of support for commercial activities and research.
4 minutes, Dr. Miller.
4 minutes. Oh, okay. Well, so I'll just say there are opportunities, many ways to participate. There are opportunities for both individuals and teams to participate in analog missions. Let's skip on. But some of the challenges, I wanted to just talk for a minute about some of the challenges faced by analog research. One is that it has traditionally been more of an experiential opportunity rather than a research-focused opportunity. There's value in that experience. There's value in the interest and the excitement that it generates, but without the addition of outputs, publications, presentations, dissemination of results, real data that you can present to show what you've learned, it's not as impactful as it could be. So one of the challenges that I see for analog research is the need to provide organized research support in order to have more scientific outputs and more dissemination of what has been learned during the analogs, so that we don't just do the analogs and have an amazing experience, but we do the analogs, have an amazing experience, and have data that we can share and that can make an impact in space exploration. I think this fits better under an organized team approach, although it can be done well by individuals as well, but certainly having an organized team approach can help to get to that, bring that research focus into play and can really develop it. I also see a needed distance from the space camp philosophy, right? If we want analog research to be taken seriously, then we need to take it seriously, and we need to, embrace the isolation, the confinement, everything that makes it a space environment, and the fact that it is a research opportunity as well as an outreach opportunity. I think that's probably, oh yeah, so I think where I'm short on time, I think I will stop there.
We are
say
done.
thank you
We
so
have
much
a half a minute. So perfect
oh,
timing.
nice. Awesome. Okay, perfect.
Anybody has any, what we can do, one quick question maybe, but otherwise this is the research station I'm the director of up in the Arctic. And we did test a Cam Smith suit up there this past year. So we are actively doing exactly what you're saying, Dr. Miller. So it's spectacular. Jonathan, I hope that answered your question. And I can't think of anything else. If anybody has any last comments. Nope. Well, we are done, folks. 3:20 in about 10 seconds.
Well, thank you all for being here.
Thanks, everyone.
And we hope that everyone has the opportunity to participate in an analog. It's an amazing experience, as Terry can tell you, as a veteran of many analog astronaut missions, and an amazing
Thanks,
chance.
everyone. Yeah. Do reach out. Any questions, anytime. Dr. Nico Gassian, thank you, my friend. Be safe. And
You're
we will
welcome. I
we'll
like
see
your
everybody
praying.
around.
Your praying hands remind me of Apollo 13.
Yeah, I remember
Oh
that.
gosh, yes. Wow.
Remember, I solved Apollo 13 by going to the trainer.
Oh,
How we
oh, that's right. Remember how he had to
solve
figure
the
out how to land.
CO2 and navigation and guidance. Just
Yeah.
one point. Can I make a quick one point? And that point is that there are certain things that analog and simulation will not do for you unless you have very sophisticated facility. On the moon, vision and glare will be a major problem. And we know that. And that we discovered from the Apollo astronaut narratives. And things that you cannot discover on analog simulation bed rests is that DVT, or venous thrombosis, that we discovered in one crew member, and the SANS, which is the visual abnormality in the astronauts, has not been shown in bed rest. And some of the experiments do not run you cannot duplicate the length of time that like 8 months in transit. So very difficult to do that, except if you have a facility like the current Mars simulation, the CHAPIA facility. So all the facilities will not give you also time progress from short exposures. I want to caution you about some notions.
Brilliant. Thank you, sir.
Really well said. Thank you. That's a
Exposing
really
people to
important point.
radiation. Exposing people to radiation costs the U.S. government a lot of money as a
Yeah, I am
result of,
concerned about that. Yeah,
it's
that's a good point.
unethical. And under Bill Clinton, we participated about the whole government exposing soldiers to atomic bomb fallout. That was a costly experience for the government. They had to pay a lot of people, and it was costly for the people who got sick with cancer. Many people. They exposed a lot of soldiers. All right. Back to you, sir.
All right, sir. I think we're done. We're gonna shut it down for the night, I guess. And there might be another show on someone next. I don't know. I can't remember. The list is long. Everyone, be safe. Thank you again for coming and listening about our research. We've been at this for many years now, Dr. Miller and I, and of course, Dr. Nico Gassian. So thank you again.
Thanks everyone for being here.
Take care. Bye.